In the previous video, we studied the first Noether theorem in field theories with the example of the scalar field for transformations that only act on the fields, or symmetries which are based on associated to transformations which only act on the fields. Now we want to see what happens with transformations that act on the coordinates, which are spacetime transformations. Okay, so there will be some transformations of the coordinates of this form, and here it is convenient to consider the tilde, the total variations of the fields under these transformations. The assumption will be that the action under consideration is invariant under these transformations, and then we will have to see what are the consequences of this by rewriting this variation in a different way, as usual. Okay, so we are considering only actions of the form d for x, and L. And this variation, now, since it acts on the x's, we'll have a term like this, plus a term like this. Okay. Now observe that this transformation of the volume element for Poincare transformations is 0. Okay, we know that this is already used here. The fact that delta tilde out L for Poincare transformations is also used here. Okay, so nothing is new, but we have to rewrite this variation in a different way. If really this is 0, but 0 written in an interesting way. So now we have to compute this variation. Sorry, I have written this variation in this way, but maybe I should write this. So we need to compute first delta of d for x, which is really d for x prime minus d for x. And in order to see what d for x prime is, we need to remember the definition that we gave for this volume element. So we defined d for x as minus 1 over 4 factorial epsilon mu nu rho sigma dx mu dx nu dx rho dx sigma, where all we need to know about this exterior product of differentials is that it is antisymmetric and linear. Okay, so if this is d for x prime, okay, we just have to add primes to these x's and apply the transformation rule of these differentials. So this is minus 1 over 4 factorial epsilon mu nu rho sigma, and then partial x prime mu with respect to x alpha, and so on until the last one, which is x prime sigma with respect to x delta dx alpha dot dx delta. Okay, now if I just take into account that this is antisymmetric, I can rewrite this as minus 1 over 4 factorial epsilon mu nu rho sigma x prime mu dx 0 and so on dx prime sigma dx3 dx 0 dx3, and because I am considering only one of the possible terms, I get a factor of 4 factorial that cancels this one. This is just the determinant, or minus the determinant because it is epsilon with the indices down, of the Jacobian matrix. And now this minus cancels with this, and we get the standard transformation law for the volume element. And here observe that this is for a completely general transformation. So I want to consider not just Poincaré transformations but any other transformations. So I will ignore the fact that the determinant of J for Poincaré transformations is just 1. Okay, so for these infinitesimal transformations that I wrote above, the determinant of J is the determinant of delta mu nu plus the derivative with respect to nu of delta x mu. Then we have d for x. And now we have to compute this determinant staying at first order in delta x mu. So the best way to compute the determinant of this object is to go back to this definition. So we write minus epsilon mu nu rho sigma, and then we would have delta mu 0 plus d 0 delta x mu, and the same with delta mu 1 and so on. Okay, for term like this, and d for x. Okay, now we only have to keep terms of first order in delta. The first term that we can consider is the product of these 4 deltas. Sorry, there is one parenthesis missing. D for x. These 4 deltas times epsilon, so this gives minus epsilon 0, 1, 2, 3. The next term will have will include this term, okay, but then the rest have to be deltas because otherwise you would have terms of higher order. So this term would be minus epsilon mu, this factor delta x mu will appear here, and then you have delta nu 1, delta rho 2, delta sigma 3, so this has to be 1, 2, and 3. But if this is 1, 2, and 3, the only possibility is that mu is 0. For the rest of the values of mu, there will be a repeated index, and this gives you 0. And then this will take the value minus 1. But let's wait. Okay, another term will include the partial derivative of delta x nu, and then for the same reason we will have epsilon 0 nu to 3 partial 1 delta x nu. Again, the only possibility for this to be different from 0 is that nu is equal to 1, and so on. And there are no more terms than these first order terms. So this is plus 1, with the minus it is also plus 1, and then what you have is 1 plus partial mu delta x mu d for x. Okay, so this is the result we wanted. Okay, and if we come up here, then we see that this is just partial mu delta x mu d for x. Okay, and we can plug this result in here. The second thing that we need to compute is delta tilde L. Now we can use the universal relation between the delta tilde and delta on L. So this just gives delta L plus delta x mu partial mu L. Why we do this? Because it will be easier to operate with these deltas, also because they are the ones that are related to the equations of motion in the end. So now we apply the standard rule to these variations, so which is the chain rule. Delta partial mu phi plus delta x mu partial mu L. This variation and this partial derivative commute, and we can integrate by parts and get the standard result. I do it quickly because we know how this works. So this gives you delta phi plus the total derivative partial L partial mu phi delta phi plus this term delta x mu partial mu L. This is what we identify as delta S over delta phi plus this total derivative plus delta x mu partial mu L, and this is the second result that we need. Now we plug everything up here in this variation of the action, and we get that delta S is was using alpha, so this is just d for x partial mu delta mu x times L. Then this is what comes from the variation of d for x. This was the factor L that we had. Now this term comes here. It is delta x mu partial mu L plus delta S delta phi plus the total derivative term partial L partial mu phi delta phi. Okay, now these two terms combine in another total derivative. Okay, I am not even assuming that the delta x mu is constant or anything. So this total derivative comes here, and we have delta S delta phi plus partial mu partial L partial mu phi delta phi plus delta x mu L, and this by assumption equal to 0. Okay, this is the formula that we were after, and let's specialize it for translation. So for translations, so let me write them. These transformations are, this is just alpha mu, and delta phi is equal to minus alpha mu partial mu phi. So now we go to this equation. Of course, since this is always satisfied, this will be the integrand has to vanish, okay, not just the integral. And okay, what we find is partial L partial mu phi and then delta phi, so this has a minus sign, alpha nu partial mu phi plus alpha mu L is equal to minus delta S delta phi. So now it's a plus because of this minus here, alpha mu partial mu phi we can take a common factor alpha nu in this equation, because alpha is constant and can come out of all this. So we have minus partial L partial mu phi partial nu phi plus I need to add here mu nu L. So when I multiply everything by alpha nu, I get alpha mu as here, and then this is equal to delta S delta phi partial mu phi. Okay, this combination here, so this clearly will be, this is true for any alphas, so we can get rid of the alphas and the brackets, and this is sorry, I'm forgetting the divergence. So this is going to be the conservation law on shell. Let me keep everything here. Okay, this object that appears here is what is known as the energy momentum tensor, and is written as the mu nu. So it is L delta mu nu minus partial L partial mu phi partial nu phi. And this is a very important object, so it deserves to be framed. Okay. And this is the energy momentum tensor. Okay, it doesn't look like a current because a current has only one index, but you see that this is actually a set of currents. So for every space-time translation we have an index nu, and we have for instance time translations, so nu equal to 0, you have a conserved current J mu. The interesting thing is that everything can be collected into this tensor, and this tensor satisfies that partial mu. Sorry, let me put this thicker. That partial mu T mu nu is equal to 0 on shell. Okay. So this is the conservation law of the energy momentum tensor, and okay, for nu equals 0, this has to be conservation of energy. For nu equal I is momentum conservation. So if T0, sorry, the mu 0 is the associated nether current, T00 is the energy density, and Ti0 will be the energy density current. Now T mu I corresponds to this momentum conservation, and so T0I is the momentum density. These are fields you need to integrate over a region of space to get the energy of that field contained in a certain region, and the momentum of that field contained in a certain region. For the scalar field, this T mu nu is easy to obtain, and it is minus partial mu phi partial, sorry, the indices interchange, phi plus a half of delta nu mu partial phi squared. Okay, so if I compute T00, for T00 I have minus partial 0 phi partial 0 phi plus a half of partial 0 phi partial 0 phi plus partial I phi partial I phi. Okay, so this is minus a half partial 0 phi. I can lower the 0 index because theta 0 0 is plus 1 in my conventions, plus a half of partial, or if you lower the indices, minus a half partial I phi partial I phi. So clearly this is a square and this is a sum of a square, so this is negative. Okay, so in these conventions that I am using, this will really be minus the energy density if we take the usual convention that energy should be positive. Now for Lorentz transformations, remember that we have now delta x mu delta x mu is equal to sigma mu x nu, and delta phi is we have computed this here, and it is minus sigma mu nu x nu d mu phi. So these are delta sigmas if we make reference to infinitesimal parameters, and what you find is of course a set of currents that now are called receive these names, so nu and rho. For every pair nu and rho corresponding to the parameters nu and rho of the Lorentz transformation, you have a conserved current. Okay, I could have written G mu nu rho. Okay, the interesting thing is that this object is also constructed from the energy momentum tensor. So this is the mu. You just have to make the calculation as an exercise. Okay, it's given by this. And it is also conserved. This is the angular momentum current density, and okay, depending on which particular angular momentum components you get, the mu equals 0 will be the density of that charge, and so on and so forth. Finally, there is a last transformation that leaves invariant the action of the scalar field, and this transformation involves coordinates and phi. So this transformation, which are dilatations, okay, consists in rescaling the coordinates with a constant factor x mu, and rescaling at the same time the fields by a constant factor omega to the minus 1/2 phi. And you can check that this in 4 dimensions, so this is for d equal 4. In other dimensions you may have different powers, that this leaves invariant the action of the free scalar field. The first thing that one needs to do is to write infinitesimal transformations. So infinitesimal is, you first have to identify when they are close to the identity. So close to the identity here means omega close to 1. So we should expand omega like 1 plus omega. Then you have x prime mu, it's equal to okay, I can already multiply x mu plus omega x mu, where omega, small omega, is infinitesimal, and then this tells us that delta x mu is just omega x mu, where omega is infinitesimal. We can call these transformations delta omega. Now phi prime is, if I expand this power, is 1 minus a half omega phi, and therefore delta omega phi is just minus 1/2 omega phi. Okay, so these are the transformations that I have to consider. Although I have written a delta, this is clearly the total transformation of phi. Okay, this is phi prime minus phi, and here I should have written x prime, and here x. Then if delta tilde phi is this, then delta phi is delta tilde phi minus delta x mu partial mu phi. So this is minus a half omega phi minus omega x mu d mu phi. This is the transformation that one has to substitute in the expression for the conserved current up here. Okay, so let's write it. This is delta partial L partial mu phi, and then multiplied by delta. So one term is there is a minus, there is an omega, and there is x mu partial mu phi plus a half of phi, and plus delta x mu. So again omega and a minus x mu L. Okay, so this will be this is just a minus omega, and these two terms x mu, well, with the signs that I have written, this will be t x, I should have written nu here to avoid confusion, sorry. Nu mu nu, the same that we wrote before, but there is an extra term here, which is plus a half of partial mu phi multiplied by phi. So in this case the energy momentum tensor appears, but there is also an additional term which is sometimes called an improvement term. Sorry, actually this sign should be minus, and this thing is the current, the conserved current associated to the symmetry under the dilatations.